Okay, so I want you to imagine a scenario. You're watching a grandmaster chess player. This person has beaten every supercomputer on the planet,
Right.
and you watch them play this just perfect, beautiful game, checkmating their opponent in 10 moves, a total genius.
Mm-hmm.
But then right after, they turn to leave the room and they can't figure out how to open the door.
Because the handle is a slightly different shape or something.
Exactly. They just stare at the handle, they seem to panic, and they just stand there frozen. If you saw that, what would you even think?
I think I was watching a glitch
Yeah.
or maybe a magic trick.
Yeah.
It doesn't compute with the genius I saw 10 seconds ago.
It feels fundamentally broken. And that is exactly where we're starting today. We're looking at a really fascinating and frankly kind of unsettling paper by Zirui Ren and Ziming Liu. The title is, Are Your Reasoning Models Reasoning or Guessing?
Which is a question I think keeps a lot of AI researchers up at night.
And we are focusing on a specific type of AI today, a hierarchical reasoning model, or HRM. Now, just to set the stakes here, this isn't some dusty academic experiment that barely works. This HRM model is an absolute beast.
Yeah, it really is.
When the researchers tested it on Sudoku-Extreme, and we are talking the hardest puzzles imaginable, the kind that make human experts cry, it absolutely crushed them.
And just to give context on what crushed means, it outperforms some of the massive, famous models we talk about all the time. Models like O3 Mini High and Claude 3.7.
Those are the heavy hitters. And the paper says those big models scored what?
Basically 0% on these extreme logic puzzles. They couldn't even touch them. But the HRM, it solved them.
Okay, so we've established we have a genius model on our hands. But here is the paradox, and this is the part that I'm struggling to wrap my head around. The researchers found that if you give this same genius model a Sudoku puzzle that's almost completely solved,
Yeah.
like literally one number missing, a puzzle a toddler could finish with a crayon, it fails.
It doesn't just fail, it chokes. It completely falls apart.
How is that even possible? It's like calculating the trajectory of a rocket ship to Mars and then forgetting how to tie your shoes.
As it does feel impossible. But what we're going to dive into today is that this failure, this inability to solve the easy stuff, isn't a bug. It's actually a window.
A window.
It pulls back the curtain on how these AI models actually think. And the conclusion the researchers come to is honestly a bit provocative. They're suggesting that what we call reasoning in these models might essentially be guessing in a very, very high-dimensional space.
That is a bold claim. We usually think of reasoning as logical steps, A, therefore B, therefore C. You're saying this model might just be vibing its way to the answer.
In a mechanistic sense, yeah. So our mission today is to figure out how a model can be smart enough for the extreme stuff, but too dumb for the easy stuff, and what that tells us about the future of AI. And to do that, we have to look under the hood. We need to talk about latent space and recursion.
Okay, let's get into the mechanics. I know HRM stands for Hierarchical Reasoning Model. How is that physically different from something like, say, ChatGPT, which I use every day?
So think about how ChatGPT works. It's a next token predictor. It generates text word by word. It says the, then it predicts cat, then sat. It's a linear stream. It's essentially thinking while it speaks.
Right. It doesn't pause to ponder the meaning of life before it answers my email.
Exactly. And HRM is different. Instead of spitting out an answer immediately, it creates a loop. It takes the input, the puzzle, and it feeds it into a hidden internal state. Think of this as like a mental scratch pad.
Okay.
It processes the information, updates that scratch pad, and then, and this is crucial, it feeds that updated picture back into itself.
It loops, so it's ruminating.
That's a great word for it. It's called recursion. It does this over and over again in what we call a latent space.
Latent space. I hear that term thrown around a lot. Can we pause and actually define what that looks like? Is the model picturing the Sudoku grid?
Not exactly. It's not working with words or numbers or grid lines anymore. In latent space, everything is converted into these high-dimensional vectors. So imagine a massive string of numbers coordinates that represent the concept of the puzzle state. The theory is that with each loop, or segment as they call it, the model refines these coordinates. It pushes the vector closer and closer to the solution.
Okay, that makes sense intuitively. It's like if I'm solving a puzzle, I look at it, I think for a second, I realize, oh, that 5 goes there. I update my mental model, and I think, again, my reasoning gets deeper the longer I look at it.
That is exactly the theory. And they use something called deep supervision to train it. Essentially, during training, they punish the model if it's wrong at any step of that loop. They want to force it to get smarter with every single revolution.
So if the theory is that it gets smarter with every loop, why does it break on the easy puzzle? If I have a puzzle with one missing number, I should be able to solve that in one loop. Why does the model crash?
And this brings us to the first massive concept of the paper, and really the key to the whole paradox, the fixed point property.
The fixed point property. Okay, break that down for me.
It's a fundamental assumption in this type of engineering. The idea is that once the model finds the correct answer, let's call that state Z star, it should stop updating. It should reach a fixed point.
Right.
Think about it. If you have the right answer, thinking about it more shouldn't change the answer, right?
Right. If I fill in the last number of the Sudoku, I put down my pencil. I don't keep staring at the paper and erasing the number I just wrote.
Precisely. That is stability. But what Ren and Liu found is that in practice, HRMs violate this property. They don't put down the pencil.
To keep erasing.
They keep churning. When the model is given that incredibly simple puzzle with one missing cell, it actually finds the correct answer almost immediately. In the first couple of loops, it has it. It knows the number.
Okay. So it wins. Why doesn't it stop?
Because it wasn't trained to stop. It was trained on Sudoku-Extreme. It was trained to bridge this huge gap from absolute chaos to order. So when it sees a puzzle that is already ordered, it gets confused. It treats the clean signal as something that still needs processing.
It overthinks it.
It overthinks it to death.
Yeah.
Because it violates the fixed point property, it keeps updating its state. It takes the correct answer, processes it again, and introduces noise.
Yeah.
It eventually corrupts its own answer.
So it overthinks itself out of the solution and ends up with a wrong number.
Yeah.
That is the definition of anxiety. It had the answer and then convinced itself it was wrong because it seemed too easy.
It's a diagnosis of the training data. The model was trained so aggressively on noise that it literally doesn't know how to handle clarity.
It's like a washing machine that's so powerful it shreds the clothes if they aren't dirty enough.
That is a fantastic analogy. Yes, it lacks the ability to just be with the correct answer.
So that explains the paradox on the easy side. It's not that it can't solve it. It's that it can't stop solving it until it breaks it. But let's look at the other side, the hard puzzles. You mentioned earlier that this looping process was supposed to be about refining the answer. Step 1, I find a row. Step 2, I find a column. Is that what's happening?
That is what we and the researchers expected. We call that incremental refinement. You'd expect the error rate to drop smoothly as the model loops. A nice, gentle slope downward, like walking down a hill.
I'm guessing, based on your tone, that is not what happens.
Not even close. The paper analyzes the loss curves, basically the error rate over time, and they found Grokking dynamics.
Grokking. I love that term. It's old school sci-fi, right? From Stranger in a Strange Land.
Yeah. To grok is to understand something so fully, you become one with it. In AI, it usually refers to a learning phase, but here, it describes the reasoning process for a single puzzle.
Okay, so what does that look like?
When the HRM is looping through a hard puzzle, the error rate doesn't drop smoothly. It stays high, it stays flat.
Flat. So for all those loops, it's making zero progress.
For many, many steps, the model is completely perplexed. The curve is a plateau. It's just staring at the problem, seemingly doing nothing. And then, bam! In a single step, the error drops to zero.
That sounds less like reasoning and more like an epiphany?
Or a guess.
It reminds me of those Magic Eye posters from the 90s, you know, the static noise.
Oh, yeah.
You stare at it, you cross your eyes, nothing happens, and then suddenly, boom, a 3D sailboat pops out. You don't get 10% of a sailboat, then 20%. You get nothing, then everything.
That is the perfect visual.
Yeah.
And this implies something massive about how the model works. It suggests the recursion isn't building a logical argument step by step. It suggests the recursion is the model guessing different latent states, trying out different high-dimensional configurations until it suddenly hits one that clicks.
So it's not solving a math problem line by line. It's shuffling through possibilities in its head until one fits the lock.
Correct. It's hunting for a stable state. And this leads us to the dangerous part of this guessing mechanism. Because if you are just hunting for a state that feels stable, what happens if you find a state that feels right, but is actually wrong?
You get trapped.
Exactly. The paper calls these spurious fixed points.
Spurious fixed points. Okay, help me visualize this. We've been talking about latent space as this abstract math cloud. Can we make that concrete? What does getting trapped look like?
The researchers visualized it using something called PCA projections, basically flattening the high-dimensional thought process onto a 2D map. So imagine a vast landscape, foggy, hilly terrain.
Okay.
The true fixed point, the correct answer, is the bottom of the deepest valley in that landscape.
Huh.
Ideally, the ball just rolls down the hill and settles there.
But there are other valleys.
Yes, there are false attractors. These are shallower valleys or little dips in the landscape.
Mm.
If the model rolls into one of those, it gets stuck. It converges. It stops updating. It thinks it's done. But the answer is wrong. This is what they call the non-trivial failure mode.
So why does it think it's right? If I put a wrong number in Sudoku, I can usually see, oh wait, there are 2 5s in this row. Why doesn't the model see that?
They analyze this using a conflict metric. Essentially, the model is minimizing a heuristic error. It's counting how many conflicts there are in the rows and columns nearby in that latent space. A false attractor is a local minimum.
A local minimum. So looking around its immediate area, everything seems fine.
Exactly. It's like a hiker lost in the fog. He walks downhill until the ground flattens out. He thinks he's at the bottom of the mountain. But he's actually just in a small dip halfway up. He can't see the real valley because there's a ridge and energy barrier in the way.
And to get out, he'd have to walk uphill first. He'd have to make his solution worse temporarily to find the better one.
And the model doesn't want to do that. It doesn't have the incentive to climb out of the hole. It just settles for good enough.
So if the model starts its guess closer to that trap than to the truth, it falls in the trap and just stays there.
Exactly.
Yeah.
This is the concept of rival attractors.
Yeah.
The truth and the lie are competing for the model's attention.
Okay, let me just recap where we are. We have a model that A, breaks simple puzzles because it can't sit still. It has no fixed point for easy stuff. B, solves hard puzzles not by logic, but by randomly guessing until it clicks. And C, frequently gets trapped in wrong answers because they look stable enough.
That is a harsh but, a fair summary.
It sounds bad. It sounds like this HRM architecture is fundamentally flawed. Why are we excited about this?
Because once you understand the mechanism, you can hack it. This is where the paper pivots from critique to solution. And this is the part that really blew my mind. Once you accept that the model is guessing and not reasoning in the human sense, you can actually design ways to make it much, much better.
If you can't beat them, join them. If it's guessing, help it guess better.
Precisely. The researchers propose a strategy called Scale the Guesses, and they came up with 3 specific solutions to fix these problems we've been talking about.
Let's walk through them. Solution number 1 needs to address the overthinking problem, the fact that it shreds the easy puzzles.
Right. Solution 1 is data mixing, or you could call it data augmentation. Remember, the model failed easy puzzles because it was only trained on Sudoku-Extreme pure noise. It had never seen a mostly solved puzzle in training.
So it didn't know they existed. It thought every puzzle was a war zone.
Right. So the researchers simply took the training puzzles and revealed random portions of them. They created what they call simplified replicates. So they fed the model hard puzzles, medium puzzles, and incredibly easy puzzles, all during training.
They forced it to practice on the easy stuff.
It sounds obvious, but it worked wonders. By mixing in puzzles of different difficulty levels, they forced the model to learn that when a puzzle is simple, it should stay stable. It shouldn't loop unnecessarily.
Did it work?
It completely restored the fixed point property. The model stopped breaking the one missing cell puzzles. It learned when to put the pencil down.
Okay, simple fix for a simple problem. But what about the hard stuff? What about the hiker getting stuck in the wrong valley?
That brings us to solution 2, input perturbation. And this leverages a really weird fact about how these models see numbers.
Weird how?
To you and me, the number 1 has a value. It means one single thing. To the model, the token 1 and the token 2 are just independent features. They're just symbols, shapes. It doesn't inherently know that 1 comes before 2.
Wait, really? It doesn't know 1 is 1?
Not in the way we do. It just knows the rules of Sudoku say you can't have this symbol twice in a row. So you can do something called relabeling. You can take a Sudoku puzzle, swap all the 1s to 2s, all the 2s to 3s, and so on.
But wouldn't that ruin the puzzle?
Logically, the puzzle structure is identical. The relationships are the same. If you solve it, you just swap the numbers back at the end. But to the model, it looks like a totally fresh input.
That is wild. So you're basically putting on a disguise.
Exactly. Imagine the hiker in the fog again. He's stuck in that shallow dip. He can't get out. So we pluck him up, swap the labels on the map, and drop him back into the landscape at a completely different starting point.
He lands on a different part of the mountain.
Right. And from this new angle, maybe he doesn't roll into the trap. Maybe he has a straight shot to the true valley.
That is clever. You're giving it a second guess. You're saying, hey, you got stuck. Try it again, but this time imagine all the 1s or 7s.
And you can do this by swapping rows and columns too. It effectively scales the number of guesses via the input. If one variation gets stuck, another might find that grokking moment.
Okay, so we have data mixing for stability and input perturbation for a fresh perspective. What is solution 3?
Model bootstrapping. This one scales the guesses using the model itself.
Bootstrapping usually means pulling yourself up by your bootstraps. How does an AI do that?
Well, during training, the model saves checkpoints, snapshots of itself at different times. Maybe one snapshot from Tuesday, one from Wednesday. Even though these checkpoints are from the same training run, they have slightly different internal weights.
Like me before coffee and me after coffee, we're the same person, but we might answer a question slightly differently.
A little bit. They found that different checkpoints tend to fall into different traps. One might be biased toward a certain wrong answer, but another might avoid it. So instead of asking just the final model, they ask an ensemble of checkpoints to vote on the answer.
Democracy for AI.
It prevents one single quirky version of the model from dominating the decision. If 3 versions say it's a 5 and one says it's a 9, you go with the 5.
So we have the trifecta: data mixing to stop the overthinking, relabeling to get a fresh perspective, and bootstrapping to get a consensus. The big question is, did it actually work? Because remember, we started with a model that was great at hard puzzles but failing easy ones.
The results are honestly staggering. We tested this on Sudoku-Extreme. The vanilla HRM, the original version, had an accuracy of 54.5%.
That's okay. I mean, better than 0, which is what the other LLMs got,
Right.
but barely a passing grade.
Right. It was flipping a coin, essentially.
Yeah.
But when they applied the Augmented HRM, combining data mixing, relabeling, and bootstrapping, the accuracy shot up to 96.9%.
Whoa. From 54% to almost 97%. That is near perfection.
It crushed the vanilla version, and it beat every other variant they tested, like the tiny recursive model. It essentially solved the benchmark.
That is a massive jump just by admitting the thing is guessing and giving it more chances to guess.
And there's one more result that I think is the most beautiful part of this paper. Remember we talked about the latent space landscape?
Mm-hmm.
The hills and valleys?
Yeah.
When they used data mixing, they noticed something about the trajectories, the path the model's thoughts took through that landscape. Before, different puzzles looked chaotic. The paths were all over the place. But after the fix, the reasoning trajectories became symmetric.
Symmetric. What does that mean in this context?
It means that different puzzles that had the same logical structure started looking the same in the model's mind. It implies the model wasn't just memorizing specific noisy patterns anymore. It had finally learned the general rules of Sudoku. It wasn't just overfitting, it was actually generalizing.
That is fascinating. By teaching it to handle the simple stuff, it actually understood the deeper structure of the hard stuff.
Exactly.
So let's wrap this up. We started with a paradox, a genius AI that failed a toddler puzzle. We learned that this failure happened because the model violated the fixed point property. It didn't know when to stop. We learned that it solves problems not by logical steps, but by grokking, guessing until it hits a stable state.
And getting trapped in false states along the way.
Right. But then we learned that by leaning into this guessing nature, by giving it more inputs, more perspectives, and simpler data, we can turn a 54% student into a 97% master.
That is a perfect summary.
But I have to ask the philosophical question here before we go. You've been very clear that the researchers think this is guessing, not reasoning.
Yes, that is their main conclusion. HRMs do not reason in a deliberate, human-like System 2 way. They rely on hunting for fixed points in a high-dimensional space.
But if the augmented HRM gets the answer right 96.9% of the time, does it matter?
That is the big question.
If I ask a human to solve a Sudoku, and they sit there sweating, writing numbers, erasing them, using logic, and then I ask this AI, and it essentially vibes its way to the answer by guessing a million dimensions at once. But we both get the same answer.
It challenges our definition of intelligence.
Mm-hmm.
We prize reasoning because it's how we solve hard problems. We build logical chains, we show our work. But maybe reasoning is just a crutch for biological brains that can't hold high-dimensional vectors in memory.
Wait, say that again? Reasoning is a crutch.
Maybe. If you could simultaneously explore 10,000 potential states and instantly recognize the stable one, the grokking moment, would you need to reason step by step? Or would you just know?
That is a spooky thought. You're saying we reason because we're too slow to just know.
It pushes us to ask, is reasoning just guessing done slowly? And if AI can do the guessing part at a scale we can't comprehend, maybe we shouldn't be asking if it's reasoning. Maybe we should be asking if our version of reasoning is just a low bandwidth version of what these models are doing.
You are leaving me with a bit of an existential crisis here.
That's what a deep dive is for.
Fair enough. So next time you see an AI solve a complex problem instantly, don't assume it thought it through. It might have just made a really, really good guess. But hey, if it's right 97% of the time, I'm not sure I care.
As long as we check its work on the easy puzzles.
Exactly. Always check the easy puzzles. That's it for this deep dive. Thanks for listening, and keep questioning what's really going on inside those black boxes.
See you next time.